So let's start. Uh, okay, let's start for uh, today's week. So this is week 5, uh, Introduction to Astrophysical Fluids. My name is Rohan, and I'm a TA for this course. Uh, I'm a PhD student at Indian Institute of Science, Bangalore. I see. So yeah, so like every week we will start with a recap of the previous week, and then we'll cover this week's material as well. So let's start with a brief recap. So yeah, so we derived the uh, fluid equations from the Boltzmann equation, which we studied in week 1, and this is how the fluid equations turned out to be. So, for example, for the first equation is the continuity equation, which states that the flux of uh, density is conserved in the fluid. The second equation is the momentum conservation equation, also known as the Euler's equation. And the third one is the energy conservation equation. And if you see that these have six variables, rho, three components of P, pressure, and energy. But we have five equations. So we need another equation to have a solvable system of equations. So these equations are supplemented with an equation of state, which is the relation between the pressure and the density and the internal energy. So we have now six equations and six variables, which can be solved exactly to obtain the unknowns, right? And given the boundary conditions and the initial conditions, we can exactly solve this for any system. Okay, now this was the ideal state, and we also saw in last week how we can get the how the equation gets modified if we have uh, non-ideal cases. Like for example, what if we introduce viscosity in the momentum conservation equation? So this gets modified with like this, and we get an extra term which is the viscous force term, which contributes to change in the velocity. Similarly, this term we get additionally to the term, right? So this is how the equations get modified in case we have some non-conservative forces like the viscous force, for example, right? Now we try to see what could be the condition um, for this fluid to be in hydrostatics. So hydrostatics is when we have, uh, as the name suggests, when the fluid velocity is zero, right, and there is no change in time. So it's in steady state completely. So del del T is zero, and the velocity of the fluid is zero. So in that case, if you look at the momentum conservation equation, so this term will become zero because del del T is zero. Velocity zero, you know, makes this term zero. So we are left with only these two forces. So this equation reduces down to this. On the other hand, the energy equation reduces down to something like this. So the physical significance of these equations is that it just states that the pressure force is actually balancing the gravity. So we also saw, how this equation is important in case of stars or stellar uh, corona, right? So we saw that in the last week how we can using this equation we can determine the pressure of the uh, corona and how it is not sufficient that the corona is static. So we need to invoke that the corona is actually expanding. Okay. So also another case that we studied in the previous week is the example of Bondi flow. So Bondi flow is when you have let's say you have some compact object and there is some other star or other gas around it. So uh, the compact object, let's say a black hole, will accrete from the gas. So the matter will fall into the black hole in a spherical manner, right? Because the gas do not have any angular momentum. So in that case, we saw that the v theta component or the angular velocity component will be zero because the velocity will only be in the radial direction. So again, if we consider the steady state case, so this will reduce down to this. Similarly, the momentum equation will reduce down to this equation. And using uh, the equation of state, which we took as a polytropic equation of state, we saw how we can come up with these different solutions, which is shown in the figure over here. So, for example, if you start with some velocity which is much less than the sonic speed, um, so the velocity will increase as we go towards as the matter falls towards the black hole, right? So we obtained by solving this equation, we obtained a solution where there has to be a critical point where the velocity of the matter is equal to the sound speed, right? So the matter has to cross this point, and in case of accretion, uh, when the matter crosses this point, right? So this is basically called the sonic point, and the velocity keeps on increasing till it reaches the surface of the compact object or the horizon of the black hole. And in that case, velocity is very close to the speed of light in case of a black hole, right? So the matter from far, it starts with a very low velocity, and you know, as it gets closer and closer to the black hole, the speed increases, and finally it crosses the point where it exceeds the speed of sound. Right? So it goes from subsonic to supersonic. Whereas in case of winds, it's the other way around. So it starts with a very uh, it starts from the you know uh, from the surface of the, let's say in case of solar wind, it starts from the surface of the sun, and as it goes outside, uh, the velocity of the wind increases, and finally it crosses the sonic point, and the velocity keeps on increasing in case of wind, right? So all these solutions, comes naturally from just these two equations, uh, the continuity equation uh, and this momentum conservation equation, right? So that was for the Bondi flow, but the thing is, these radial flows are not very real in astrophysical systems and practical astrophysical systems, because in nature we always see systems which have some non-zero angular momentum. So everything is rotating and they have some angular momentum. So when the matter has some angular momentum and there is no external torque applied to it, it cannot it has to conserve the angular momentum, right? So for that, we don't see radial fall into the black hole, right? So we see matter which are falling, which have some angular momentum, and if it has some angular momentum, it will fall in a circular path, or more like a spiral path into the black hole, like radially, and it would form a disc-like structure instead of a. So yeah, then we moved on to the thin disk approximation. So what if the matter falls in kind of a in the form of a disk, right, in a spiral path? So choose cylindrical coordinates r, theta, and z. So there are some assumptions which we will take, and then we will apply these assumptions onto the onto these equations of the fluid equations, and then we'll solve these fluid equations using these assumptions, and with kind of solution we get. So, okay, so let's look at the assumptions first. So, as we are saying that, uh, one assumption is that since the matter is falling, in a spiral path or in a circular manner, so there is not much change in the theta direction, right? Also, the v theta should be much greater than the vr, because the matter is not falling radially, so the radial velocity is much less. And similarly, we'll assume that there is no velocity in the z direction, that is in the vertical direction. Also, the change of Vr and V theta in the z direction should be negligible. So this is what we had covered till the last week. Let me know if you have any questions. Otherwise, we will start with the material for this week. All right. So yeah. Okay. So we will basically solve these equations with the assumptions, with these assumptions. But before that, we will take a little detour, and we will see something uh, else which will be important in our case. So, yeah. So we will try to see how viscosity can play a role in these kind of flows, right? So, okay, let's start from the very basic. So let's say you have some uh, imaginary 2D, 2D rectangle in the fluid. And let's say that, Mm, there are pressure forces acting on it. So what are let's do the you know force balance for this block of fluid. Okay. So there are pressure forces acting on it, and well, will ignore gravity for now. And and apart from pressure forces, in presence of viscosity, so there are also viscous forces acting on the fluid. Right. So so to understand how viscosity, um, you know, play a role, and how does it manifest in producing a force on the fluid, we can think of this block as having a velocity structure, which follows this kind of a relation. So the u is dependent on y. Y is this vertical direction, and t, of course, and the y and z component of u is 0. Okay, so the x component of u, which is in this direction, depends on the y, only the vertical direction. So basically, what it says is that in you can think of this block as a layer of sheets, right? The many sheets, and all those sheets fluid will have different velocity, which varies from one sheet to another. Now, if different sheets have different velocity, so what will happen is that when the fluid is trying to flow past, uh, so it will experience some forces from the bottom sheet as well as from the top sheet. So let's say the top sheet has a higher speed, so it will try to drag the bottom sheet along with it, right? On the other hand, if the top sheet has a lower speed, it will try to, slow down the surrounding sheets with it, right? So this is how exactly the viscous force acts, right? So the viscous force is kind of a drag force which tries to, speed up or different layers in the fluid, and therefore it depends on how the this you know this velocity u varies with this y, or in different sheets how it varies, right? So the viscous force can be then assumed to be mu del u del y, and this mu is the coefficient of viscosity. So this is just some constant factor. So as we saw that the force is proportional to del u del y, right? And Yeah, and okay. Okay, so this is not the force. This is we can say the shear stress due to the viscous force actually. So we'll see how the what is the force exactly, and this is just a proportionality constant, right? So similarly on the top surface, the shear is basically mu del u del y at y plus del y and times delta x, which is the length of this segment, right? Okay. Now, okay. So now let's calculate. So if we just consider these two forces, the pressure force and the viscous force, we can see that the pressure force is basically given like this, right? In this total volume, it is like this, and this can be written as dp del p del x del y, right? So what is the pressure force acting on this surface? So this is given as this. Similarly, we can write the viscous force from the stress that we calculated over here. And this will turn out to be mu del square u del square y del x. So this is actually the uh, you know the force due to the viscous stress, and it is given by mu del square u del square y. And this is how the the momentum balance equation will transform in presence of some viscous forces, right? Okay, so okay, so now we know that the viscous forces have plays a role in you know in the momentum balance equation. So we need to take care of that also when we are doing uh, the accretion disk simulations. Right? So, okay, now another way to look at it is that, um, okay, so in case of solid body rotation, so by solid body rotation, I mean when the whole object has a uniform angular velocity, right? So, for example, if we have any solid object, and if we rotate it, the whole body and basically all the particles will have equal angular velocity, right? So in that case, the velocity is given as omega cross r, right? And if you calculate this component del v del x, so we already know that the shear stress depends on this factor del u del y, right? So yeah. So now we want to see that does the whole part of del u del y contributes to the shear stress or just some part of it? So we would like to just to calculate the shear stress and which is basically the pi ij, and we want to see which part of this del u del y contributes to the shear stress. So we'll just go to the notebook and we'll try to derive this expression and we'll see how we come with this. So, okay. Okay, let me start from here. So, as I was saying, for solid body rotation, V is OI plus R. So, before that, we saw that the shear stress is proportional to del Vi del Xj, right? Now, del Vi del Xj can be written as del Vi del Xj plus del Vj del Xi plus del Vi del Xj minus del Vj del Xi. So this is half of this. So why we are writing it like this? So because as we saw in the last lecture that this is the symmetric part which we write as lambda ij, and this is the antisymmetric part which we write as pi ij. Well, you can write it as anything, but the main point is that this is the lambda ij is the symmetric part, phi ij is the antisymmetric part. Now, why we are uh, you know why we are breaking it into symmetric and antisymmetric part, that we will see from this solid body rotation. So in case of solid body rotation, as I was saying, that since the all the fluid particles are moving with the same angular velocity, so there is no shear stress in case of solid body rotation, right? So in case of solid body rotation, so there is no shear stress. So we would like to see what will happen. Uh, you know, mm, yeah. So basically, we would like to see if we are getting zero pi ij for solid body rotation, or we are getting something which is non-zero, right? So ideally, we should get zero for pi ij if it's a solid body rotation. That's what I'm trying to say. So Vi will be epsilon ijk omega j xl, right? And del Vi del xj will be epsilon ijk omega j delta jl. So this will become epsilon ijk. Well, delta jl will mean that j is equals to l. So this will be ilk omega j. Similarly, if you calculate del V j del xi, so if I write Vj, it will be epsilon j ik epsilon j, well, let me write it as jki omega k xi. This will become epsilon jki omega k. Well, this k are dummy indices, so I can change it to well, this, yeah, because of delta JL, this will also become L in this other part. Okay. Okay. So K and J are dummy. So J I can represent it as well. Okay. So here let me write this down as J only. Right? Because J and L are equal, so I can write either way. So here K is a dummy index. So I can write it as Okay, let me write it this way. Let's put this. Okay. Yeah. Now there is a property of this Levy-Civita symbol, which states that ijk equals to minus of jki, right? So it turns out that these two terms cancels. Okay. So if you add these two terms, they will cancel. So what the conclusion is that this lambda ij is zero for a solid body rotation, whereas phi ij is not zero for a solid body rotation. So since we want that, the shear stress to be zero for a solid body, we uh, we would therefore require that in the shear stress only the lambda component should stay and the phi component shouldn't stay. So therefore we conclude from here that pi ij is equals to lambda ij and not this phi part. This antisymmetric part is not considered in the shear stress. So that's what I meant over here. Okay. So this was also derived in the lecture, and you can see the argument over there as well. So yeah, now in the previous lecture we also saw that this pi ij is a traceless tensor. So this is lambda ij, and in order to make this traceless, we have to subtract the trace of this vector, which turns out to be like this. Right? And as I said, so this is the shear stress. To obtain the viscous force due to the shear stress, we have to, force is just stress dot the surface area of the fluid. So this will give you the total force, viscous force, right? So finally, you will obtain this equation, right? So this is the full equation that we will use while studying the thin accretion disks. Okay. Okay, so that was a little detour, but uh, what our what we will do now is we will try to use the thin disk approximation, right, which is over here, and try to apply it to the fluid equations, and we will try to see what kind of solutions we get from this. Okay. Okay. So, any questions so far? All right. Okay. So, yeah. So, we already discussed what are the approximations that we are going to take. Now, let's just start with the basic continuity equation that uh, we write already. Okay. So, okay. So one thing to remember is that these equations are written in vector form. Okay? And if you so for example, v dot del v, what will be the radial component of this equation? What will be the uh, azimuthal component of this equation? So, for example, if you're trying to write this equation in you know, in spherical coordinates or in cylindrical coordinates. So this equation will become very complicated. So in the reference, I have mentioned one book which is Accretion. So in the previous references also I have mentioned that book. So it's called Elementary Fluid Dynamics by Accretion. Okay, so in that book, you can find out what will be the form of all these equations in different coordinates. So in the appendix, I don't remember which appendix, but in one of the appendix, so they have expanded all these equations into in different coordinates, cylindrical coordinates, spherical coordinates, and so on. Okay. So there you can find how this vector equation reduces to these uh, equations and Yeah, basically you will get different components of this equation. Okay, so right. So this is how the how the continuity equation will reduce to, right? So del rho del t plus 1 by r del r of r rho p r equals to 0. Now here we do one, well, trick, you can say, just to remove the, you know, the z coordinate um, from the equations, because that is not very important in this case of thin disks, because they are like geometrically thin and they don't have much thickness, which we'll see later on why don't have much thickness. So in order to do that, we define another quantity which is sigma, which is integration of rho dz, right? So now what we do is we integrate this equation with dz. So basically, you can take the integration inside, and if you do rho dz, this will become sigma. Similarly, you do this and you do rho dz, you will get again sigma over here. So this equation will reduce down to this. So this is the simple thing. Okay. Similarly, now if you expand the theta component of the momentum balance equation, which is given by this, okay, well, actually not given by this, more like given by this, because here we also consider that mu is a function of radius, right? So if you expand this equation and if you look at the theta component of that equation, that will turn out to be something like this. So again, this is given completely uh, in the Atchison book that I mentioned, right? So the derivation from here to here in different coordinates will be a little bit more, you know, complicated, but we don't have to go through it every time. So yeah, but the theta component of the equation will turn out to be this equation. And yeah, so again we integrate with dz, right? So this will again reduce down to this equation, right? Also, this mu is basically mu integration dz, right? Okay. Uh, yeah. What else? Yeah. Okay. So that up to this, it is pretty much simple, right? But then we can further simplify this equation to obtain this equation. So now this derivation from here to here is not done in the lecture. So I thought maybe it will be a good exercise to just do it once so that we can follow the steps from now. So because this is a very simplified form of the expression, we are going to use this again to derive something which is important as well. Okay. So let me open. So let me first write down all the equations. Okay. Yeah. So these are all the equations. So this is the continuity equation, this is the momentum balance equation. Now using these two equations, we have to derive this third equation. So what we will do is that we will multiply the first equation with r, and we will multiply this equation with r v theta, right? And if we do that, we are supposed to get this equation. So let's actually check this out. So let's go from uh, this equation, and if we uh, let's break it down and see if we get these two equations. So first thing to note is that you see that these equations have v theta and this equation has omega. So first thing to see is that v theta is always omega r, right? That we know. Now this equation also has a d omega dr. So d omega dr could be written as d theta of v theta by r, which is 1 by r dv theta dr minus v theta by r square. Okay. So we're just writing down this. We will use this thing later on. Okay. Now let's break down the first term. So the first term is basically r v theta del sigma del t plus r sigma del v theta del t. Right. So I'm just replace this omega with v theta by r. Okay. So if you replace this by v theta by r, so r will cancel. So let's write this term. So this term will become sigma r v theta. So we're just taking ddt of sigma r v theta. So just chain rule. Okay. So this is what the first term gives. Now let's look at the, well, let me this first. We're gonna need some more space. So now let's look at the second term. So the second term is 1 by r. Okay. So before looking at the second term, I just want to write down one uh, identity that we are going to use. So del R of RF. SF. So this is just an identity that we can use later on. So for example, there are many terms which are of this form, right? So 1 by r del R of r square fr. So just using chain rule. So mm, this will be del r square by r times del f del r plus uh, 2r by r fr. So we can write it like this, right? Okay. So yeah. So why we are doing this? Because let's say this term. So in this term, if we apply this, well, let's see what will happen if we apply this. So let's look at the second term. So the second term is 1 by r del r of sigma r cube omega dr. So well, omega is, as I said, v theta by r. So we can write this as r square v theta. So now this term has reduced to something of this form. So 1 by r del del r of r square times fr. So here f is just sigma v theta vr. So if we just apply the above formula, so we will get so first del del r of rf. So del del r of rf. So f here is sigma v theta vr. I guess you can identify that plus f is just sigma v theta. Yeah. So we can even break down the first term like this, just using chain rule. R sigma vr plus r sigma vr del v theta del r plus the f term. Yeah. So this is what becomes of the second term. Okay. Now let's look at the third term now. So third term is 1 by r del r of mu sigma r square del v theta del r minus mu sigma r v theta. Yeah. So here, if you just put this thing d omega dr, this value. So by third term, I mean the term on this term. So if you just put d omega dr as this value, you will get this thing. And we can simplify this again using that using this expression. So del r mu sigma r del v theta del r minus v theta plus, well, let me first actually expand this a little more. So, okay, so here what we have, so we can do one thing. So we can take mu sigma common from both the terms. Since both the terms have mu sigma, we can take this outside. And then using chain rule, we can first do the derivative of mu sigma, and then we can do the derivative of the rest of the term. So let's see how it looks like. So if we just do the derivative of mu sigma first, so you will have del r of mu sigma, and inside the bracket you will have, so this r will cancel with one r over here. So this will be r del v theta del r minus v theta. Okay, so the second term. And now we will do mu sigma times del r of the rest of the thing. And the rest of the thing is r square del v theta del r minus r v theta. Okay. So now, yeah, now we will keep this term as is. We will expand this term. So if you see, uh, yeah, that's what we will do. Let's do it. So again, this term will be as is. Uh, we will look at the second term, which will be okay. So I've just written this term like this. Is that right? Right. Oh yeah, there is a 1 by r uh, extra over here, so I missed that in that. So there will be 1 by r over here, 1 by r. Yeah, now it makes sense. Yeah, so basically this. Oh, okay, yeah. Uh, okay. Now we will just expand this term, the last term. The first term will be as is, and if we just expand the last term, so we'll get mu sigma del v theta del r is r del square v theta del r square plus del v theta del r minus v theta by r minus del v theta del r. So this will cancel. And now we have a lot of terms. Okay. So now let's just check. So we have this first, second, and third terms of this equation, and let's just check that whatever we are getting, is it matching with, you know, this first equation multiplied with r plus the second equation multiplied with r v theta. So for example, the r v theta d sigma dt is this term, right? So let's mark it. So this term is accounted for. Next is this term r sigma del v theta del t. So that is well, okay. Actually, I made a mistake. So the first equation should be multiplied with r v theta, r v theta. Second equation should be multiplied with r. Yeah, yeah. So let's check that if we get that. So yeah. So r sigma del v theta del r sigma del v theta del t. So that is this term, and this term is basically this term multiplied with r v theta. So these two terms are accounted for. Now from the second term, we get this thing. So v theta del r of r sigma vr. So that is exactly this term, right? Multiplied with r v theta. So r will cancel. So v theta del r of r sigma vr. So that is this term. So this term is also accounted for. Now this one is r sigma vr del v theta del r. So that is this term again. So this is also there. And sigma v theta vr. So that is this term. So this is also there. Okay. Now from the third term, we will have uh, yeah. So del r of v sigma times r v theta dv theta dr minus v theta. So this is this term, right? If you multiply it with r, so this term is this term. So this is also accounted for. And if you look closely, so this term is basically what you get from here. Okay? Right. So basically, the point is that this equation is basically this equation multiplied by r v theta and plus this equation multiplied by r. So it's a messy calculation, but I think this kind of exercises are good for seeing things. And okay, so so why this? Why do we have to reduce this equation into this? So if you see, so from this equation we can by uh, taking the assumptions of the thin disk. So for example, what assumptions? By assumptions, I mean if you remember in our previous week we derived something. So for example, omega, it varies as r to the power of minus 3 by 2. So we can take omega as a function of r, right? Like this. And so if you take omega as a function of r, and similarly, if you neglect Vr with respect to omega, which is very small, so you can get a very good approximation of the sigma as a function of radius and time. So sigma is a function of r and t. Given the initial conditions, you can obtain the value of sigma. So one such thing is done for this kind of a system. So in this system, what it says is that there is a disk only at r equals to r naught. So basically, it's a ring, and we would try to see, given this initial configuration, initial condition, we'll try to see how this sigma evolves in time as well as in radius. So we saw that this evolves something like this. This evolves according to this. So this was already shown in the lecture, and the physical meaning of this solution is actually very important. And it states that, if you start with a ring, the ring diffuses and it spreads over such that there is more mass which is getting accreted, and there is a less mass which is going out, taking out the um, angular momentum from the system, right? So so this is how can see that viscosity can play a major role in the evolution of such systems. So for example, this tau factor is directly proportional to viscosity. So if you have a greater tau, so if you can see from this expression that this is exponential of -1 by tau, right? So if the viscosity is more, the spreading of the matter will be more and more, right? So also as time goes on, as T goes higher and higher, the matter spreads more and more and becomes a flat structure rather than the sharp one, which was at the start, right? So this is how viscosity plays a role in diffusing the matter and forming the disk in this kind of systems. So this example is just for a ring, but in general, for a general disk with a given initial condition, you can always solve this equation to obtain this sigma as a function of r and t, and you can obtain more realistic. So you have to solve this numerically given the initial and boundary conditions, and by those numerical simulations, you can see how the disk evolves in space and time. And that is what actually people do, and there are a lot of research papers on these kind of systems, and people still do research uh, in these accretion flows. Any questions? Okay, so okay, well, let's move on to how these disks can how will be the structure of these disks in steady state. So again, by steady state, I mean there is no evolution in time. So del t is basically zero. So you can just take this equation and remove I mean take the term which contains the time derivative to be zero, and you will be left with this term. Similarly, you can do this for this equation as well. So yeah, now we want to see something. So if you remember here, we only looked at the theta component of the momentum equation. So for example, this equation. So this is a vector equation. So this will have three components: r component, theta component, and z component in cylindrical coordinates, right? So we didn't look at the r and the uh, z component, right, of this equation. So now we'll look at the r and the z component, right? So the r component will reduce down to something like this, right? And if you see that, we are neglecting the viscous term over here, and this has a physical, uh, reason behind it. And the reason is that, these disks, as I said, were Keplerian disks, right? Or, the or thin disks, right? So the matter is almost like in a Keplerian orbit. Okay. So in the radial direction, there is not much viscosity. The viscosity plays a major role in the phi direction, because in the phi direction only there is a difference in velocity between the two layers, right? So as I was talking in the first slide, that the viscosity is basically just the viscous force arises from the difference in velocities between the two layers of the fluid. So the difference in the layers of the fluid are only in the phi direction. So there is not much difference in the layers of fluid in the radial direction. So we can safely neglect the viscosity in the radial component of this momentum equation. Similarly, the z component of the equation, we can write it uh, in this form. And again, we are neglecting the viscous term. So now from this equation, from the z component, we can like do a order of magnitude calculation. So del p del z, we can approximate as p by h, where h is the height in the z direction, right? So if we just use this equation, so this will be p by rho h equals to gm z by r cube. So z, as I said, is the height, h by r cube, and from here we can obtain that the h square by r square is of the order of r p by gm rho, right? So these order of magnitude calculations are very important in astrophysics, and sometimes when you can't, calculate, or let's say you don't want to calculate some quantities, exactly, uh, you have to, in order to calculate these quantities exactly, you have to do a numerical calculation, like, right? So if you want to, avoid a numerical calculation, and if you just want to see the order of magnitude of some quantities and see whether we can neglect some quantities or not. These kind of calculations are very widely used in astrophysical systems. So similarly, from this we can get that h square by r square is proportional to rp by gm rho. And as we are saying that these are thin disks, so therefore h is much less than r. So the height of the disk is much less than the radius, and they are like geometrically very thin. So this h by r ratio should be much less than one, right? So what we get from this, like, are there any terms which we can neglect? So using this approximation, we try to look at these two terms, right, which are in the radial component equation, right? So if we just look at these two terms, so these two terms, if we just do a similar analysis of the order of magnitude, so this will be 1 by rho p by r and divided by gm by r square. So this will turn out to be of the order of h square by r square again, and this will be much less than 1. So what this says is that this term is much less than this term. So this term can be neglected in case of, in a thin disk approximation, right? Also, similarly, we also saw, like, if you look at the assumptions, here VR is much less than P theta. So again, similarly, we can neglect this term compared to this term. So ultimately, the radial component equation basically turns out to be V theta square by R equals to Gm by R square. Now, if you look at it, so this is exactly the same equation that we saw for Keplerian motion in our previous week, right? So if we have, let's say, so yeah, so this, if you solve that equation, your omega will turn out to be something like this. So yeah, so this is the just the Keplerian equation, Keplerian motion equation, which states that the centrifugal force is balancing the gravitational force. So you can see just from from this thin disk approximation, the radial momentum balance equation gets reduced to something very simple, which we already know. Right? So yeah, so yeah, like, to conclude that, I would say that these two equations doesn't give anything new, but um, it's interesting to look at the consequence of thin disk approximations, and how these equations confirm something that we already knew. Okay. Okay. Now, interestingly, now what we'll do is we will take this equation, which is the continuity equation, and this equation, which we derived from the continuity and the momentum balance equation. Now we'll look at it in the steady state. So as I said, in the steady state, del t is 0. So here del t will be 0. So you're left with this term. So del r of something is 0. So that means if derivative of some quantity is 0, so that means that that quantity is constant, right? So similarly here del r. So this, if we can combine both these terms within the derivative, so this plus this, whatever is inside, will again be 0, and therefore the inside part is basically constant, right? So that's what I have written. So this part is constant, and this part is some other constant, right? Okay. So yeah, now what is it, so now we try to look if there is any physical significance to this constant, right? So if you remember in the last class, in the last lecture, we saw mass accretion rate for Bondi flow, which were like spherical flows. So in that case, we also saw that the mass accretion rate is basically proportional to the flux of matter that is coming in through a shell at radius r. So that was for a spherical flow. The shell radius was 4 pi r square, and the mass flux through that is rho v, right? So in this case, since it is not a spherical flow, the flow is a thin disk kind of structure. So if you see this, so this is rho dz, right? The sigma is rho dz, and 2 pi r sigma vr is will again give you uh, you know the mass flux um, through a surface at that radius r. Okay. Right. So this is just 2 pi r rh. So if you see the cylinder, so what is the surface area of the cylinder? Surface area of the cylinder is 2 pi rh, right? If you consider a cylinder of height h and radius r. So 2 pi rh times the flux of density, which is rho v. So that is basically the mass accretion rate. So sigma is, if you remember, it's rho dz. So it can be, estimated to be rho h. Dz is just the height. Okay. So yeah. So this C1 has the physical significance. 2 pi C1 is just the mass accretion rate. So C2. So let's see if what we can make of C2. So now here is an argument is that so whenever I mean the mass is falling into the black hole, or let's say any other compact object, so when the matter reaches the surface of the object, so there is no more uh, shear, right? Because it has already reached the surface, and it's not part of the disk, it's going into the black hole, right, through the horizon. So the angular velocity, the change of angular velocity with radius is no more there. So this term will vanish, right? The second term will vanish. So at the surface of the star, which I denote as this asterisk symbol. So the C2 will be sigma star r star cube omega star v r star. Okay? And now we want to see if we can relate this C2 with some known parameters like m dot and r star. So I will derive this, how we get C2 from here to here. Okay. And so we see that. So, yeah. But any questions so far, let me know. So here, what would we do? We did R sigma VR equals to C1. M dot is minus 2 pi C1 equals to minus 2 pi R sigma V R, which is just the mass accretion rate. Right. And C2 is sigma star R star cube omega star VR star. Okay. So as we saw, 2 pi R sigma VR. So if we can just separate 2 pi r sigma VR and then divide by 2 pi, we are left with r star square omega star. Yeah, that's right. So, okay, sorry, I'm not sharing this. Okay, yeah, sorry. So r sigma VR is C1. So m dot is 2 pi C1 is 2 pi r sigma VR, and C2 is basically sigma star r star cube omega star VR star. And we are writing this as this thing. So multiplying and dividing by 2 pi and separating out this part and this part. So such that this part will become m dot, right? So actually minus m dot. So minus m dot by 2 pi times r star square omega. So if you remember from our last week, omega is gm by r cube, square root of that, and we'll just use that, and by using that, we'll just get this thing, gm r star for half. Okay. Now, how to get a relationship between this the viscosity parameter and the mass accretion rate from these equations only, right? So that we'll see now. Okay. So let me write down the this conservation equation once. So, okay. So let's see. Okay. So this is C2, and C2 as we saw is m dot by 2 pi gm r star whole to half. This is new by the way. Okay. So now we want to see if we can obtain a relationship between nu and m dot. So as I said, we will just replace omega everywhere with gm by r cube, square root of that, which is true for Keplerian rotation. And if we do that, let's see what we'll get. So mm, okay, so this is- so this part, as we said, that r sigma VR is basically m dot by 2 pi, right? So if you just separate out r sigma VR, you are left with r square omega, which is gmr whole to the power of half. So if you just put the value of over here of omega, why is it not writing? Okay, now it's coming. Yeah. So if you just put the value of omega, so r square omega is gmr to the power of half. Okay. So the first term will become this term will become m dot by 2 pi gmr to the power of half. The second term will be mu sigma r cube del omega del r. Let's keep the second term for now as is. Then minus m dot by 2 pi gm r star whole to the half. Okay. So this is at the surface of the star or the horizon or whatever you take. Right. So d omega dr is minus 3 by 2 gm to the power of uh, gm to the power of half r to the power of minus 5 by 2. So we will use this value and just replace this d omega dr with this thing. Okay, where did it go? Okay, did I lose it? Yeah. Okay. Now just putting the value 3 by 2 mu sigma gm to the power of half r to the power of half. So this 5 by 2 and there is always already an r cube. So I'm writing this term over here. So mu sigma, so this 3 by 2 gm to the power of half and r to the power of 3 minus 5 by 2 will give you r to the power of half. So this equals m dot by 2 pi gm to the power of half r to the power of half minus r star to the power of half. I just took these two terms on the same side. So there is r to the power of half minus r star to the power of half. Okay. So from here we can just easily get mu sigma equals to m dot by 3 pi 1 minus r star by r to the power of half. Right? So you just keep mu sigma. So gm half cancels. So this thing cancels. And you just divide both sides by r to the power of half. So this one will become 1 minus r star by r to the half. Okay. Okay, so that was fine. Any questions? Okay. So now we want to see. So what is the physical meaning of this thing, this expression? So basically, what it says is that if you have uh, higher mass accretion rate. So by higher mass accretion rate, I mean that if there is more flux of matter falling into the black hole or the accretion disk, so you would require a larger viscosity, right, to transport that matter. So basically, it says that viscosity is directly proportional to the m dot. Right? So more the flux of matter, more is the viscosity. Now, as I was saying, that viscosity is just the difference between the velocities in two layers of the flow, right? Now, if you think of it like that there are two layers of fluid which are moving past each other. So there is some, you know, friction between the two layers. Well, maybe friction is not the right word, but there is some dissipation of energy between the two layers due to this viscous stress, right? Because one layer is going over the other and there is some uh, you know uh, energy that is getting dissipated between the two layers, right? Because the layer with a higher velocity will try to drag the layer with the lower velocity, and in doing so it is doing some work. It is uh, you know expending some energy, right? So what is the energy that is dissipated by this viscous force. So as we earlier saw, the viscous stress is proportional to mu del u del u del x or del y, whatever. So so the viscous force is proportional to mu del omega del r. So omega is just v theta by r. So we can easily think of it as del v theta del r as well. Okay. So it is how the theta velocity of the layers, change with radius. So so there is a short, I would say, uh, well, derivation that was done in this book, which I have um, in the reference. So this is the book by Kundu Cohen, which states that the viscous force, the work done by the viscous force, or if you see this term phi, so this is the rate of viscous dissipation. So this is actually equal to mu Eij plus 1 by 3 del dot u delta ij whole square. So this Eij is basically the what you call the lambda ij or del Vi del xj. Okay. So so as you can see, the work done by the viscous force is mu del Vi del xj whole square. Okay. So this is exactly what I have written. So later on, like you can look at this derivation and see how it comes about. But for now, you can just uh, think of it like the viscous force is doing some work, and the work done or the energy that is dissipated is directly proportional to the square of the difference in velocities between the two layers, right? Which is the viscous stress, and it is proportional to the viscous stress. So anyway, so this turns out to be something like this: mu r square del omega del r whole square. Okay. And yeah, so as we know from uh, yeah, so like as we said that mu is nu sigma, so nu sigma r square del omega del r whole square, right? And you can replace nu sigma with this thing which you already derived, and the energy dissipated is directly proportional to m dot, right? And if you calculate the luminosity, so luminosity is just the energy times the uh, or the flux uh, times the area. Okay, so this is 2 pi r dr. So this is energy dissipated uh, times the all the over all the radius, right? So 2 pi r dr from r star to infinity. So in that case, you will get this thing. So this, if you integrate this, you will get this thing. So this is exactly equal to the gravitational potential energy, or the half of the gravitational potential energy of the matter that is being accreted, and the rest of the energy is basically translated into the kinetic energy of the matter that is accreted. So yeah, so this energy which is being dissipated in due to the viscosity is basically dissipated into the fluid as in the form of heat. So this is used to heat up the fluid, right? And the fluid becomes hot and it emits. Generally, in this kind of thin viscous systems, you can assume this systems to be of black body, and because they emit this black body radiation, right? And which are of typical temperatures of 10 to a 6 or 10 to a 7, like that in case of stellar mass black holes. So um, yeah, so the viscous dissipation is dissipated into the heat of the in the system, and then this heat is getting radiated, which you see as this bright light in this kind of systems, which comes out as light, and then you see those accretion disk around the black holes, and that is exactly I mean sort of similar to what this EHT, Event Horizon Telescope images have captured, right? So as the accretion disks. Okay. So yeah, any questions? So yeah, so this is the end of accretion disk discussion, but there are like lot of literature on this, and this is an active area of research. Um, and actually, I'm also currently doing some work which is related to this viscosity and how it leads to turbulence in this kind of systems, and how those turbulences, you know, necessary for transporting the angular momentum and all this stuff. So these are all current topics, and you know, you can look up many research papers on this. Yeah. Okay, so moving on to the next topic, which are sound waves. So, okay, so again, we go back to the our basic continuity equation and the uh, momentum balance equation, and we do uh, we do s- something called a linear stability analysis, right? So this is a very important, this technique of doing this linear stability analysis is very important and is used in many applications of fluids, right? So what we do is in that technique is that it's very simple. So we take a flow. So in any flows, you can approximate the flow as some mean flow of the fluid, and then within that mean flow, so you can think of some perturbations in the flow, right? So let's say you have some, a fluid flowing in a straight line, and there is no at constant velocity, at constant density, and everywhere it's smooth and perfect. Now, if you introduce some, perturbation to the fluid, right? So small perturbation, which causes the density to fluctuate from the mean value, right? So those perturbations are basically represented over here as rho one, right? So these are under the assumption that rho one is much much less than rho naught. So rho naught is the base density of the fluid, or the mean density, and over the mean density you observe some perturbations of the fluid, right? So now the question is like why we are doing this linear stability analysis. We want to understand, like, if we perturb the fluid, is the fluid gonna end up, completely, perturbed, disoriented, and doing all sorts of crazy things, or it will, like, if we introduce the perturbation, the fluid will, smoothen out the perturbation, and then again, go into, something which which it was before, like a smooth flow, right? So and if the perturbations, grow with time, at what speed do they travel in time, right? So that's also what we want to understand, because these, for example, like the accretion systems we studied. So these are highly, nonlinear systems, and there could be some perturbations in the fluid, in this accretion disk, which could, you know cause all sorts of turbulence, and which could lead to very turbulent flow, and which actually happens, right? In practical situations. So so this is an important technique to do these kind of studies. So again, so like I was saying, that the rho is rho naught, the mean density, and over that we introduce a perturbation. Similarly, for pressure, we introduce a perturbation. For velocity, we would assume that the velocity, just for simplicity, you can also assume a v naught here. But for simplicity, we will assume that initially the fluid was at rest. So you can just assume that, water in a container or something. And then you give a velocity perturbation to it, right? So now, you know, if we replace, so for example, if we put this rho equals to rho naught plus rho one in this equation, and this p, yeah, so p is not there in this one, and v equals to v1 in this equation. So this will reduce down to this. Okay. So yeah, I guess you can visualize how we get from this to this. If not, just let me know. I will do it in the notebook. But for now, I am assuming that you have understood this. So Similarly, for the second equation, if we just put the values of V as V1, P as P naught plus P1, and rho as rho naught plus rho 1, you will get this equation, right? Now we also know that we have to apply the equation of state, which is P k to the k rho to the power of gamma. And again, if we, uh, put these values over here, we'll get P1 equals to Cs square rho 1. Okay. So basically, the perturbation in pressure is equals to the perturbation in density times the speed of sound. Okay. Speed of sound, if you remember, is just del P del rho. Okay. In case of an adiabatic, sorry, in case of a polytropic gas, it's the root over of speed of sound is gamma p by rho, square root of that. Okay, sorry. Yeah. So using this and using these two equations, so if you just take another del t of this equation, so we'll get del square rho 1 del t square plus rho naught del dot del v1 del t, and if you replace del v1 del t with this, so you'll get this equation del square rho 1 del square t equals to c square del square p1 rho 1. So if you understand, like if you look at this equation, so this is basically a wave equation, right? So if you have learned about electromagnetic waves, so they also follow a similar equations, right? So the electric fields and the magnetic fields will follow this kind of equation. So this just means that the perturbation, this rho 1, that the perturbation that you introduce in the fluid will travel as a wave, right? And the speed of the wave is basically Cs square. Okay. So, yeah, so that's what it says, that any perturbation that you introduce in the fluid, it will travel at the speed of sound, and that perturbation will travel from one part to another, and then so if you look at, let's say, if you look at 2 points in the fluid, what does it physically mean? That's what we're trying to understand. So if you look at 2 points in the fluid, if you introduce a perturbation at the first point, and the second point is further enough such that if you look at the second point at a time such that the perturbation has not traveled to the second point at the speed of light, so CST is not enough such that the perturbation will reach this point, so you will not be able to see the perturbation at the second point at that instant of time, because the perturbation travels at the finite speed. Okay, and it might not reach the second point. So as I said, that this rho 1 is basically a wave, has a follows a wave equation. So for a wave solution, we can estimate rho 1 to be e to the power of I k dot r minus omega t. So this is a standard solution of a wave equation, right? So if you put this solution over here, you will directly get the relation omega square equals to c square k square, which is called the dispersion relation. So this is a similar relation that we also observe for propagation of light in vacuum. So similarly, we can calculate the phase velocity, which is omega by k, and the group velocity del omega del k. And for a non-dispersive fluid, uh, we will get both same, right? Okay. So, right. Another thing that we can see from, you know, this equation, the second equation. So again, we can put V1 to be like this. And if you just look at this equation, so if you just do del P1, so also you can write P1 similarly in this form. So del P1 will be uh, IK P1. So let me just show this, how V will be parallel to the K, the wave vector. Right? So I guess I can show it over here on the side. So there's a small step that you can do. So for example, the equation was del V1 del T equals to minus del P1 by rho naught. Right? So V1 is V1 naught e to the power of I k dot r minus omega t. So del V1 del t will be minus omega V10 e to the power of I k dot r minus omega t, which is minus omega V1 again. So similarly for del P1, uh, so if P1 is P10 e to the power of I k dot r minus omega t, so del P1 will be uh, Ik times P1. Okay. So if you just put this equation, so you will get minus omega V1 equals to Ik P1 by rho naught. So basically V1 is this k vector times some. So these are all constants, right? So V1 is proportional or parallel to k. So that's how it comes. So this is just a small calculation that you can always do to see uh, how it is. So, for example, so this gives us that the sound waves are longitudinal waves, right? Um, unlike electromagnetic waves, which were transverse waves, because this V in the electromagnetic waves was would turn out to be so the electric and magnetic fields would turn out to be perpendicular to this direction of propagation k. But in this case, the direction of propagation is parallel to the velocity of the fluid. So now we define um, another variable, which is Mach number, which is v by cs of any medium. So v is the fluid velocity, cs is the speed of sound. So now, why is this important? Is because as we are talking that this perturbations travel at the speed of sound in a medium, right? So what if the Mach number is greater than 1? Okay. So that it means that the speed of the fluid is, greater than the speed of sound, right? So, so basically it says that the fluid is moving at a, faster speed than the speed of sound. So the information that the fluid has been perturbed is not even uh, reaching to another point before the fluid flows to that point, and it creates the perturbation more, right? It enhances the perturbation and the fluid becomes unstable, right? Because the time scale to smoothen out this perturbation is basically cs sorry the um, basically 1 by cs is inversely proportional to cs, because the information in the fluid is propagating at a speed of cs. Now if a fluid is moving at a higher speed, I mean, you can understand that the information is not reaching to that point, right? And before that the fluid is creating the perturbations and making it unstable. Whereas if the fluid is moving slowly enough such that the perturbations, the velocity of the fluid is low enough such that you know it gets enough time to get smoothen out, such that the speed of sound is more than the velocity of the fluid. So it will get enough time to get smoothen out, and the perturbations will be smoothened out at the speed of the sound. Okay. Yeah, I hope that is clear. Any questions so far? Okay, if not, we'll move on to the last part of today's lecture. Okay. So, okay. So in the previous analysis, so here, if you remember, we ignored this term because we wrote this equation by ignoring this term, because this will give out nonlinear effects. So for example, v is v1, so v1 dot v. So yeah, this will turn out to be v1 dot del v1, right? So this thing. So this will introduce, second order terms in v1, which we are earlier neglecting. Now we want to see what if we include the second order terms, which we if we keep this term, and we will see what will happen. So for example, this equation in one that this is zero, right? So this equation is what is called the Burgers equation, right? Basically, inviscid Burgers equation because there is no viscosity. Because similarly, like the viscous Burgers equation as well. So why we are studying this is that we want some phenomena that occurs in these kind of fluids very often, like even in this accretion systems or in this supernova, which we'll study in the next week. So uh, this kind of situations arises very often. So these are what are called shocks, right? So I'll explain what does a shock physically mean. So if you look at this graph, so let's say your velocity profile is something like this, the black curve at the starting of the uh, at t equals to 0, basically, right? Now, this equation is the inviscid Burgers equation, right? So, for example, so this is, let's say, your V1, right? Now, we want to see how this, velocity profile will change with time as we go on increasing time, right? So, let's look at this region of the graph, right? So, this region of the graph. So, first, you must note that velocity is positive everywhere, right? But the derivative of velocity is del v1 del x. So that is positive in this side, this region of the graph, but negative in this region of the graph. Okay. So this term is negative in this region and positive in this region. Now, just write, if I just take this term on the this side, so you'll have del v1 del t is equals to minus v1 del v1 del x. So that means that how, if you want to see how v1 changes with time, whether it is increasing or decreasing. So if this term is positive, if del v1 del t is positive, so that means v1 is increasing. If del v1 del t is negative, so that's simple. That's what we are trying to look at. So as I said, this side has negative velocity. Okay. So this means that uh, del v1 del x is negative on this side. So the velocity, the del v1 del t will be negative. So that means it will decrease, right, with time. So for example, if you look at this point, whereas on this side, the velocity will go on increasing. Okay. So if you follow this pattern, well, okay, I think I did the reverse. Okay, there is a minus over here. So if you yes, so if you take this term to the right, the velocity of on this side, all the points on this side will actually increase, right? So this is what is represented in the next time step. So this velocity will increase, whereas this will decrease. So as we go over time, so what will happen is that you see that all these points decreased. So this is at the next time step. This is again at the next time step. So this velocity will keep on increasing. This velocity will keep on decreasing until it flattens out and it forms something like this. So at this point the velocity has decreased, and at this point the velocity has increased. So this will occur a sharp transition in velocity, uh, which we call as shock, right? So yeah, is it clear? I don't know if the explanation is clear, or should I expand on it more? Anyway, so the shock is what we call as I mean, the physically, if you see, it is just a very drastic change in the velocity at this point, and this is what we call as the shock front, right? So we'll have very rarefaction material over here. So the matter will be very rarefied over here because the velocity of the matter is decreased over here, and the velocity has increased on this side. So all the matter will accumulate at the shock front, right? At the transition point, right? And the matter will become dense over here, and there is sharp fall in velocity as well as density and pressure and all those parameters, which we'll see later on how those parameters behave at the pre-shock and the post-shock region, right? But this is what is shock is basically. So you see a sudden drop in density, velocity, temperature, pressure profiles at this point, right? So yeah, so this is what we saw from this inviscid Burgers equation. We just saw it qualitatively by just looking at the derivatives and how the velocity at which point will increase or decrease, and that will give rise to this kind of a shock feature. Right? So, okay, and these shocks are also well seen in these kind of astrophysical systems. So now, to understand how the velocity, pressure, and temperature or density, how they varies across the shock boundary, so we try to see from this diagram that you see. So, for example, this is the pre-shock and this is the post-shock region. So, if you just draw the boundary of the shock over here, and you see that the matter is going from the pre-shock to the post-shock region, and if you assume, so this is again going back to our previous lecture, so where we derived the conservative form of the equations, maybe V3, yes, V3 would derive the conservative form of the equations. So this was the conservative form of the equation, right? So if you look at the this form of the equation, if you just well, there is no time variation, so this will go to zero. So this will be conserved, right? So this flux, which you call flux inside this gradient, will be conserved across the boundary of the shock, right? So rho v across the boundary will be conserved. So pre-shock versus post-shock will be equal. Similarly, this term will be equal, and similarly, this term will be equal. So this is what we conditions, right? So this is the rho one u1 in the pre-shock region should be equal to the rho two u2 in the post-shock region. Similarly, the momentum flux and the energy flux will also be conserved in the pre-shock and the post-shock regions, right? So from this equation, we want to understand how the density and the velocities, pressure, temperature, how they vary from pre-shock and post-shock. So this is how these conditions are. If you solve these equations, we'll get these things. So this is M1, the basically the Mach number. So U1 versus CS1 and rho 2 and rho 1. So what is the ratio of rho 2 versus rho 1, which is equal to the ratio of U1 versus U2? That is obviously you can get from this equation. And that is equal to this. So we'll derive this equation, how it comes. And similarly for pressure P2 versus P1, how the P2, in the post-shock region, pressure is dependent on the pre-shock region pressure. And P is proportional to rho KT. And that's how we also get the temperature in the post-shock and the pre-shock region. So let us derive this equation just to see that we can get these equations just from these three equations, right? So, see. So let me write down the Rankine-Hubert conditions. So those are so 1 square is equal to 2 plus 4 2 to square half v1 square plus epsilon 1 plus v1 by rho 1. Okay, so these are the Rankine-Hubert conditions. So if you remember, So for ideal gas, pressure is related to gamma minus 1 rho epsilon, right? And so basically epsilon plus P by rho, we can write it as, so epsilon we can write as P by gamma minus 1 rho plus P by rho. This is equals to P by rho into 1 plus 1 by gamma minus 1, which is equals to gamma P by rho times gamma minus 1. So gamma P by rho is Cs square by gamma minus 1. Okay. So we can simplify this like this. So basically this equation will turn out to be half U1 square plus Cs1 square by gamma minus 1 plus 2 half U2 square plus Cs2 square by gamma minus 1. Did I get the questions right? Let me check once. Okay. Okay. So now from 1, we get U2 square equals to rho 1 square by rho 2 square U1 square. From 2, we get rho 1 U1 square plus P1 equals to rho 1 square U1 square by rho 2 plus P2. So what I did is that I kept rho 1 U1 square plus P1. So P2 plus rho 2 U2 square. So I just replaced U2 square with this thing. So now let's look at 3. So these are 1, 2, 3 by the way. Yeah. Well, 3 is this one, this one. Okay, so from 3 we get half of E1 square minus 1 by rho 1 square by rho 2 square plus CS1 square by gamma minus 1 goes to rho 1 by rho 2 gamma minus 1 CS1 square plus gamma by gamma minus 1 rho 1 by rho 2 U1 square 1 minus 1 by rho 2. So what did I do is that, so I just replaced U2 square with this thing. So this half U2 square I just replaced with this thing, and I just brought this one to the other side, so you get this term, right? So this will become then equal to this thing. Let me check. CS. I wrote Yeah, that is supposed to be the case. Yeah. Okay. Yeah. This will come. Now, what we'll do is that we'll multiply this equation with 2 times gamma minus 1 and divide it with CS1 square. And this is the step where we will use M1 equals to U1 by CS1. So this will come out to be M1 square gamma minus 1, 1 minus rho 1 by rho 2, 1 plus rho 1 by rho 2. So I'm just breaking up this term as 1 minus rho 1 and 1 plus rho 1 by rho 2. And multiplying with 2 gamma minus 1 by CS square, this will term become 2. This will be equals to 2 gamma. Uh, wait, wait a minute. Yeah, so this will be equal to, let's see, plus 2, 1 minus rho 1 by rho 2 equals to 2 gamma rho 1 by rho 2 m1 square 1 minus rho 1 by rho 2. And simplify this. This will be gamma minus 1 m1 square 1 plus rho 1 by rho 2. Just dividing throughout by 1 minus rho 1 by rho 2. We'll get this 2 gamma m1 square rho 1 by rho 2. And this will be m1 square gamma minus 1 plus 2. Okay. Let me see. Gamma minus 1 plus 2 equals to rho 1 by rho 2 m1 square 2 gamma minus 1. So finally rho 2 by rho 1 will come out to be m1 square gamma plus 1 by n1 square gamma minus 1 plus 2. So what we try to see from this equation is that, so I think the consequences of this equation are more important than the derivation. So here, if we, see that m1 goes to infinity, so that is high Mach number. So the velocity of the flow is very high compared to the speed of light. So in that case, rho 2 by rho 1 will be gamma plus 1 by gamma minus 1, which is a finite value. So at the shock, rho 2 and rho 1, so these values, rho 1, well, also if you can see that rho 2 is greater than rho 1. So, okay, so I think, well, in this case, the shock is like the velocities are in this direction, right? So that means the flow is going from right to left. So rho 2 is greater than rho 1, but the jump in the density is finite. Whereas if you look at the pressure relation, for example, P2 by P1, and if you try to put M1 tends to infinity, so this will come out to be infinity. So there is an infinite jump if you take M1 to be infinity again. So there is an infinite jump in pressure, whereas there is a finite jump in density. So why there is an infinite jump? So because as we know that pressure is proportional to kT, rho 1 kT1, right? Also this rho 2 by rho 1 is although finite, this T2 by T1 is not finite. So that is what is causing an infinite jump in the pressure of the across the shock. So it just means that the shock front is basically heating up the material, as we were also discussing earlier that this the shock front is depositing a lot of heat into the post-shock region, such that the temperature of the region will go up, I mean, blow up, and it might go to infinity. And it is heating, this temperature is basically going to infinity, which is causing the pressure jump to be infinity as the Mach number goes to infinity. And also from here you can see that if Mach number is equal to 1, so that is V equals to Cs, then rho 2 will become rho 1. So there will be uh, no difference in the density. So the fluid will become, uniform across the shock region. So, so these are two extreme cases. So Mach number is equal to 1, fluid will be uniform. If Mach number goes to infinity, there will be a finite jump in the density, whereas an infinite jump in the pressure and temperature. So yeah, that's it for shocks. So this is how it behaves. We'll In the next week we'll look into more detail how the shocks play a role uh, in different astrophysical systems. But I guess I hope you got the concept clear, like how the shocks behave and all. And again, these are the references. So, for example, for the viscous part, I find this book pretty good, and they derive the fluid equations from very fundamental principles. For the accretion part, you can always look at this book. And as I said, so this Atchison is a book on fluids. So this has good explanation about the sound wave part, and also how you can write all the equations, uh, uh, like the fluid equations in different coordinate systems. So this is a good reference for that. So, any questions so far? Anything related to assignments or anything else? Okay, if not, we can then end the call. We'll again meet next week, same time. Yeah, thank you.